Hey everybody, it's Ripley. I'm back again. We're going to do some hypothesis testing around means this time rather than around proportions. I'm going to show you guys a little trick I learned on this. This is pretty cool. So I'm going to go to my bookmarks and I bookmarked that one page. All right, so check this out. Remember, what we did before is we did tests around proportions. We did it with this guy right here and we did it with this guy right here. Remember, for this guy, we did not get a significant result. In other words, the p-value was not small enough, so we did not reject the null hypothesis. Remember, you choose to reject or not to reject. On this guy, I believe, we rejected because the p-value was small enough. Remember, if the p-value is less than alpha, or if you end up with a critical value that's larger than a test value that's larger than the critical value, then you chuck it if it ends up in that critical region. Then that's called a significant result. Lots of vocab, lots of terminology. It'll move quick, but I promise we'll clear that up. So here's what we're going to do. We're going to test this guy right here with some information. We'll do this guy first. All right, which was basically the average garbage household uses less than 30 pounds of garbage per month or year or whatever. All right, and we're going to test this sucker. Now, let's go back to that page that I had. I get to use my handy dandy new tool. All right, and there are some assumptions, and our assumptions are as follows. So to be able to test means or assumptions, hypotheses about means, we have to have the following. One, you got to have a random sample, all right, or an SRS, simple random sample, at best, and we're going to know sigma, all right. If we don't know sigma, we got a whole different set of issues that we're going to talk about in here. Don't worry about it, okay? All right, so you ready? Let's see. Here was the problem. What we had is we had a null hypothesis that the mean was equal to 30 pounds of garbage per month, and we had an alternative hypothesis that the mean was less than $30 per month. Let me go ahead and check that just to make sure. Go to this guy. Yep, we're good. There we sit. So we're good there, and that's what we're going to test. All right. So, oops, excuse me. Let's go back here. And this is what we know. All right. I know that I'm sorry, it was in a week. All right. So I'm just pulling this thing out of my ear right now. So we're going to say that N equals, there were 62 households that were tested, and they had an average of 27.443. Now you may say, Ripley, I'm already looking at this. 27 is definitely less than 30. But the thing I want in your brain is this. Was this 27 pounds? Was this far enough away from 30? In other words, you're going to get variation just caused by random distribution, of these 62 data values. However, the question is it far enough away? And we're going to build the whole thing out, all right? There are two ways to solve this guy. There isn't the third, because notice, we can't use confidence intervals because this is a less than. Confidence interval, I probably shouldn't do that because it looks like a less than or equal to. Confidence intervals can only be built when the alternative hypothesis is not equal to. Okay, and we know from past data that the standard deviation for everything is 12.458 pounds. Now we've got some information. Look at that. Let's check this out. Standard deviation is huge. It's 12 pounds. Now, if we were just doing a regular old z equals x minus mu over sigma, if this was a single data value, right? If this was just one household, look, this is well within one standard deviation away from the mean. It's only 2.5 pounds away from 30, and the standard deviation is 12.5 pounds. However, remember, we're talking about sample means here, so we're going to do sigma divided by root n. Remember this standard error of the mean, okay? Now, I'm going to do this two ways. Let's see. Let's draw our picture first. Let's do the critical region, the critical value, and then the test statistic. And then when we're done, we will, because we can sort of kill two birds with one stone here. And we're going to determine whether or not we can, remember, everything is around the null hypothesis. Can we reject it or not? But we're missing one piece of information, and that's our alpha. And I'm going to pick alpha equals 0.05 again. I'm going to get y'all nice and used to using alpha equals 0.05. It's like I said, it's kind of the union standard. That's what they, excuse me, I got dry throat today, so bear with. All right, now, you ready? Here we go. Let's draw ourselves a picture. All right, so I'm going to draw myself a nice normal curve because we know that sample means distribute themselves normally. All right, and let's see. Our claim is that the mean is 30. Notice that's what our null hypothesis says. Okay, and what we're going to do is we're going to find a critical value, CV. Now, you got to remember, in the back of your brain, every time you see a normal curve, you better be thinking standard normal curve. So there's a little zero up there because this test statistic right here enables us to go from any curve to the standard normal curve. So let's figure out the critical value right now if I want this area right here to be 0.05, which is what alpha is. Okay? That's the first thing that we're going to do. We're going to find the critical value because I know, I'm going to shade that thing in because it's fun to do on this thing. I know that that area is going to be 0.05. Now, what we're really testing here, ladies and gentlemen, is we're testing whether this value right here is a value that is reasonably caused by randomness. All right? So let's check first and foremost. I'm going to pop out. I'm going to go to my good friend, my Z table, and I'm looking for, this one's nice because it gives us that value underneath, right? I don't know if you know what I mean by that, but it gives me these probabilities below. So I'm looking for 0.05 in here, right? Ooh, it looks like it's going to be 1.645, right? 1.6, 0.0505, 0.0495. Yeah, right down the middle. So 1.645. Okay, so when we pop back over, I've got our little curve here. Sorry about that. I had a little bit of technical difficulties. It was a little hoopty. All right, so I've got, remember, I stumble over here. I got my value here to here, right? So it's 1.645, actually negative because it's on the left-hand side. So I know that my critical value here is going to be Z equals negative 1.645. Now, here's the easy part. Watch this. All I'm going to do is, this is my critical value. Sometimes you'll see this as a Z star or a Z sub CV. Whoops, CV. All right, I'll typically write it as a Z star and just makes it easy. Or I'll forget to write it and it doesn't really matter because this right here is going to be our test statistic that we're going to compare. Okay, so Z equals X bar, which is 27.443 minus mu, which is 30, divided by, let's see how much of this I can do in my head. Not at all. 12.458 divided by the square root of 62. Now, remember, you got to be real careful when you're doing this in your calculator. There's nothing more of a bummer than screwing something up when you're trying to get it all in there. Having a perfect conceptual understanding of what's going on and then have some computational error pop up. It's very frustrating. So what I typically do with these is I'll go 27.443 minus 30, and I'll hit enter. And then I just take that and divide, because then I can do parentheses and I don't get all screwed up. So 12.458 divided by second square root of 62. Let's see, imprint, and my answer is negative 1.616, or approximately negative 1.62. Now, I'll show you why I wrote that in just a sec. So let's do this guy right here. My test statistic, make them blue. My test statistic is negative 1.62. It's, notice, this is Z equals negative 1.62. Now, ask yourself, does it end up in the critical region? The critical region is defined by everything to the left of the critical value. It doesn't make it there. So what is our conclusion? Well, it's simple. All right, and there's lots of ways to do this. Because, or since, however you want to write it, because Z equals negative 1.62 does not end up in the critical, I'm locked up, the critical region, i.e. another way to write this, negative 1.62 is greater than negative 1.645. I'm going to show you something a little shiesty about this here in just a sec. We don't have enough evidence to reject the null hypothesis. All right, it appears, if you think about it, if I can't reject this guy, then it appears, I forget what the claim was on this. Whatever the claim was, the claim could have been, well, it equals 30, or that it's less than. I think the claim was that they consume less than 30 pounds a week. Incorrect. There's not enough evidence. I can't reject the null. Now, some of you may be going, really, what? That's pretty close. Negative 1.62 is real close to negative 1.645. Now watch this. I'm going to change. Watch what happens. What if instead I were to let alpha equal 0.1? Okay? Now, what does that mean? Alpha equals 0.1. That means that I am going to, well, let's go look. If I want alpha equals 0.1, what does that say about my new critical value? Critical value. What does that say? Well, let's pop over to our table. And if I go, let's see, I'm looking for 0.010. What's the closest thing to where is that guy? Right here. So 0.01. Now I'm at negative, I'm sorry, 0.1, right? Not 0.01. 0.1 gets me, where are we? At 0.1, that's 0.1. Negative 1.2, negative 1.2, well, we'll call it 1.28. Okay, so let's go back here. Watch this. My critical value, this is an implication arrow, by the way, is going to equal negative 1.28. Now, think about that. What just happened? Had I picked a weaker alpha level, 0.1, instead of 0.05, then this would have been negative 1.28. Let's see. That would put me right about here, right? This is negative 1.28. Then my test statistic would have ended up to the left and would have ended up in my new critical region, okay? So what you're looking at here is, I mean, if somebody doesn't publish their alpha level, which you are supposed to, everybody's going to ask you if you come up with what are referred to as significant results. Significant results means that you are significantly different from the null hypothesis. If you come up with significant results, they're going to want to look at your alpha. But if you're just showing the layperson, yeah, there appears to be a significant difference. It appears that we are using significantly less than 30 pounds a week. Well, yeah, it's because your alpha level is huge. In other words, this doesn't allow, think about that, this allows for 10% of the data values to be at least this extreme, right? Now that may sound strong, but it's really not. It's a very weak premise.